I have put up problem set 6, I guess. It's all about, it's all based on material that we have now covered, the world of air and motion. So it's, you should be ready to work on it whenever you like. It's due next Wednesday, November 2nd, in class. Let's see. So with the transition from airplanes to wood stoves, we're leaving behind the discussion of fluids. At least fluids will show up, but not directly the same way. And going over to the story of heat. And so the section on wood stoves, and it's also water, steam, and ice, and clothing, insulation, and climate, is all about sort of the movement of heat from place to place. Subsequently, we'll go on to talk about really manipulating heat, working with it in intelligent ways, or well, at least sophisticated ways. And that's the world of what's known as thermodynamics, the movement of heat. So it's a series of a progression of topics. And so the topic of wood stoves is really just sort of an introduction to the world of heat and how it moves about. So my opening question is, which is more effective at heating a room, a black wood stove, a shiny gold wood stove, or that they're essentially equal? Okay with the question? How many think that it's a black wood stove is most efficient? How about a shiny gold wood one? Or how about both being equal? Okay, so about 50-50 split between black and equal. And just I'll give away the answer because when we get to the answer, really, it's pretty far down the road. I might not make it today. It turns out the black wood stove is the winner. And it's the winner for sort of an unexpected reason. It turns out that the black wood stove glows more brightly, black though it is, than the gold wood stove. It's better at emitting heat by way of what's known as thermal radiation, which is a form of light. Or it's a type of light. You can't see the wood stove glowing. It appears black to your eyes, but if you could see in the infrared, you would notice that it's just brilliantly glowing in the infrared. A different part of the spectrum one we can't see, and so that's part of the story I have to talk about. A shiny gold wood stove, on the other hand, is especially bad at emitting thermal radiation. Shiny metals, it turns out, are not good at emitting thermal radiation, and in the infrared, gold is probably the best choice for something that doesn't emit thermal radiation. So it's not very efficient at sending out thermal light. Okay. So some observations about wood stoves is that they burn wood in an enclosed firebox. So they're an improvement, I suppose, on fireplaces. All the details in that are less important than the creation and delivery of the heat. They have long chimney pipes often, and that is part of the delivery system for heat. Their surfaces are usually dark in color, and that's related to what I just talked about. That it turns out shiny metals are not so good. Black is not as black as you may think it is, and for interesting reasons that we'll come to. Obviously, you burn yourself if you touch these things. They have very hot surfaces, the wood stoves. The heat rises off the surface in the upward direction, so we have to talk about that. If you put your hand over the stove, you feel something you don't feel when you put your hand in front of the stove. And they still, if you do stand in front of the stove, out of this rising heat, you still feel hot. And why is that? And so that's part of the story. Okay, so the questions we'll pursue, and the first one here is what are thermal energy and heat? And I started talking about that last time, but now I will sort of try to do it more completely because I was pressed for time. Both thermal energy and heat are disordered forms of energy. They're the same old energy. And I told you this way back when. They're still kinetic energy and various potential energies, gravitational, elastic, all the standard potential energies. They are just chopped up into minuscule portions and distributed statistically. And the fact that they're distributed statistically and consequently disordered makes them much harder to work with, or more literally, they are unable to do work directly. They're no longer equivalent to work. And this is jargon that physicist jargon is equivalent to work. What does that mean? It means that certain types of energy are directly capable of doing work on something. So they're equivalent to work. It's like the energy in a battery, the electrical energy, is equivalent to work because with the right objects around it and stuff, you could do work with it. You can run a motor that then pushes things, and there's a simple transformation sequence that ends up doing work. Something high in the air has gravitational potential energy that's equivalent to doing work. It's equivalent to work, and so on. Thermal energy is not like that. You can't, there's no straightforward sequence of gadgets that will turn thermal energy into work. It will turn out, you can still, you can do work with thermal energy, but you need some other source of order to make up for the fact that thermal energy itself has no order. And we'll see later on that thermal energy, when you've got two objects that are different temperatures, there's some order in that. And that allows you, the presence of two different temperatures allows you to convert some of the thermal energy back into work. That takes place under the umbrella of the laws of thermodynamics, and we'll do that. So like a car engine is what's known as a heat engine. It's using the flow of heat from a hot burn gas to a cold outside air, and that's got some order in it, and it's therefore able to do some work. All right, so thermal energy is disordered. It's all chopped up into pieces. You can't directly do work with it. It's responsible for temperature, and so we've talked from time to time about temperature, and it will turn out that temperature scales, the whole concept of temperature, is built around the idea that heat flows from hotter objects to colder objects. For statistical reasons, it basically lives in the world of mathematics more than and statistics rather than any particular physics, any particular universe. It would be the same in other universes with very different laws of physics. They might still have things like heat that flow from hotter to colder objects. All right, what else? So thermal energy is what's in an object. Heat is what moves between them. It's just a technical, wordy distinction. It's just like energy is what you have. Work is how you transfer it mechanically. This is like thermal energy is what you have. Heat is how you transfer it thermally. Years ago, I used heat interchangeably. Heat to describe an object contains heat and an object transfers heat, and the purists would get after me for not drawing a distinction between having and transferring. Is that okay? Can you see the distinction between having thermal energy, transferring heat? That's the way it is. Okay, so first issue is a wood stove, you put stuff inside, wood, for example, your old textbooks, whatever. I guess you don't put those back in. You go over to the bookstore and sell them back. But you put them all in, whatever they are, and you ignite them. And that whole process, what's happening there, assuming that you got the fire started, you are converting something into thermal energy. And how's this hell happening? Well, you're taking wood and you're taking air. You know from experience you don't have air present, stuff doesn't burn. Something in the air is involved. And you're rearranging those materials to end up with new materials and thermal energy. And so the story of this, just to name things, the various components that you're burning and that are produced after the burning is done are typically molecules, which are collections of atoms. So some of this stuff I sure hope is review from long past. The world's composed, objects in the world are composed of atoms. Sometimes the atoms are free on their own, wandering around. For example, in the air, there are atoms of helium. They're pretty rare. There are atoms of argon, more common than helium, but for a lot. And others that are just independent, and they really rarely get involved in any permanent attachment to anything. So they're around as atoms. But pretty much everything else in our world is atoms that are stuck to each other. And there are various ways in which they stick to each other in various contexts of, for example, a chunk of metal, a big piece of aluminum is to some extent one giant assembly of atoms all stuck to one another. So to describe it. You would not describe it as built out of molecules. It's just one big collection of atoms all stuck together for particular reasons. So there are materials like that where they're all stuck together, and then there are materials like the air we're breathing right now, in which there are a very limited number of atoms stuck together. For example, 2 nitrogen atoms are stuck together, or 2 oxygen atoms, or 1 carbon and 2 oxygen atoms stuck together as a carbon dioxide molecule. So a first thing to deal with is what is holding those guys together? And the answer is chemical bonds. And you've surely encountered chemical bonds somewhere in the past in your previous schooling. And what I want to make sure at this point is that you have some sense for what a chemical bond is. I mean, you can name it. It's been named for you all these years. Ideally, you come away from this understanding pretty much what it consists of. And so I'm going to illustrate a chemical bond using 2 atoms, if you will. Have to be baseballs. But the idea is this, that atoms at great distance from one another, we'll just get rid of gravity. It's just not an important part of the story. 2 atoms that are far, far apart don't care about each other at all. They're just independent little particles, oblivious to one another. But if they get closer together, and how close is close? Well, atoms have sort of an approximate size. That's also a fuzzy, that's a complicated story, but you can imagine they have a sort of a size you could assign some meaningful size to them. When they start getting a few atomic diameters apart, they begin to attract each other. And that's universal. That's every atom will attract every other atom when they first begin to notice each other's presence. The forces that show up are attractive. This one attracts that one, and as required by Newton's third law, or in accordance with Newton's third law, the second one will attract the first one. They're very weak attractions, but they're there. At great distance, it almost doesn't matter what the atoms are. Those attractions are just sort of generic. As they get closer, the attractions get stronger. And now it becomes dependent on the exact choice of atoms. They begin to sort of notice which, are you friend or foe, that kind of stuff, okay? So they begin to attract more strongly. And at a certain separation, they reach peak attraction. The forces get strongest. And then as they get closer, the forces begin to diminish until eventually the forces drop to 0. So there is a point, a separation, which the force drops to 0, and they are in equilibrium. Right? If they get closer than that, the forces become repulsive. Again, this is it's a generic property. It happens for all atoms, this sequence. The only question is whether it gets a little more complicated sort of in the middle ground and how strong those forces get. But eventually when they get too close together, they begin to repel. And you can think of this as they're essentially overlapping with one another and too much. A little overlap turns out to be part of the process of attracting each other, but a lot of overlap is bad news for them. They hate it. So the forces go from nothing to slightly attractive, to more attractive, peak attraction somewhere, less and less attraction, 0, that's equilibrium, and then repulsive and gets worse and worse and worse with no limit. Okay? So imagine you take 2 atoms. So we'll play atom tweezers. Suppose I've got two tweezers holding a pair of atoms without bothering them except to just keep them in place. And we start to bring them toward each other. Well, they're attracting one another a little bit. By about now, they're starting to attract. So if I didn't hold on to them, they would accelerate toward each other and go faster and faster. So let me not release them. Let me hold on to them and let them pull my tweezers together. They're doing work on me. Right? I am pulling outward on them, and they are moving toward each other. So I'm doing negative work on them. They're doing positive work on me. They're pulling my hands toward each other. So they're giving me energy. They get closer and closer. They pull extra hard, and then they start getting weaker and weaker and weaker. And I go to the point where they are at equilibrium separation and no longer pulling on me. And then I set them down. Stay there, guys. And leave. I walk away. Think about what happened. They did work on me as they went toward each other the whole way. I took them all the way until they got to equilibrium when they're no longer pulling on me, and then I let go and walked away. I have stolen energy from them, right? They did work on me. I've got it. They don't have it. I snuck off with it. They're now bonded together, and what they're bonded together with is a deficit in energy. If they want to go back apart, somebody's got to come in and undo the theft that I just did, theft of energy. Somebody's got to come in, grab the two of them, and now pull them apart. The forces reappear, get stronger, peak, get weaker, 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 weaker. That whole process of pulling them apart requires energy. It requires work to be done on them, pulling them apart. So when they were at this equilibrium separation, they are held together by a deficit of energy. The amount depends on the specific choice of the atoms and stuff, but that's what a chemical bond is this energy deficit. To get the system apart, you have to repay the energy deficit. And different pairs of atoms will experience different overall deficits of energy, and so you basically can look on anywhere online, and you could find bond strengths. What bond strengths mean is how much energy you have to repay to get these to pull these two atoms apart and take them off in principle to as far as you want apart. And they range from exquisitely small, for example, something like a pair of helium atoms. I'm not sure a pair of helium atoms actually has any bond strength, but certainly two neon atoms, for example, or two argon atoms. It takes an exquisitely small amount of energy to pull them apart. So little energy that they barely stick, and therefore a little thermal energy will be enough to repay the debt, and they go apart. So that's why things like liquid helium is really cold, but liquid neon, liquid argon, these are really cold gases. They're cold liquids because you have to get you have to have so little energy around to pull the bonds apart. In contrast, things like pulling apart oxygen, hydrogen, or hydrogen, a pair of hydrogen atoms themselves too, or a pair of oxygens or nitrogens, they take a lot of energy to pull apart. They're really stuck, seriously stuck. And there are different ways in which the attractive forces show up, and there are different labels given to the type of chemical bond, and some of these you've encountered in chemistry. There are ionic bonds, which involve an exchange of electric charge. There are covalent bonds, which involve a sharing of electrons. Metallic bonds, which involve a vast sharing of electrons and stuff like that. Okay, so that's a chemical bond, deficit of energy. Any issues with that, or things you wonder about with that? All right, given that, when you go to the wood stove and it's burning, it is starting with chemicals, which you can just give them a name. You can call them reactants. They're incoming chemicals, ones that are going to be consumed, and they're going to be converted into product molecules, which is what's going out. And the key point in all this is, if you look at the energies in the bonds that you start with, you sum them all up, there's a certain deficit of energy. So that when you sum it all up, you end up with a negative number, and it's a certain value. And once the burning is over, you have another bunch of molecules form, so they have bond energy in their bonds, which is a negative number, a deficit of energy, and it's a bigger deficit. The point of a reaction that releases a lot of thermal energy is you started with reactants that were held together by a certain group of chemical bonds, and you end up with product molecules that are held together with chemical bonds that are stronger, that involve releasing even more energy to form those molecules. And the missing energy now, the extra that was removed from these molecules to leave them extremely tightly bound together, that missing energy has become thermal energy. Is that okay? So if I just light a match here, I'll light a candle, rather than lighting a piece of wood just to keep the smoke down, what we're starting with in this case are molecules that resemble those in wood. Wood, incidentally, is nearly the vast majority of what's in wood is a polymer molecule known as cellulose. Cellulose it's a giant molecule. That's what a polymer means, in effect. Polymers consists of of many repeating small molecules, or a pattern of repeating small molecules, all stuck together with strong bonds, covalent bonds, so that the whole thing is one giant molecule. You can walk from one end of the molecule to another very far away across, always traversing strong bonds. And so cellulose is a polymer molecule built out of smaller molecules that are sugars, the sugars you're familiar with. And so cellulose shows up. It's by far the most common polymer in nature, actually in the world then. Cotton is almost pure cellulose. And it's sugars that are held together, and what else about it? We can't digest it. Although it consists of sugars that by themselves we could digest, and we would even find sweet, we don't have the machinery, the molecular machinery, to snip apart the sugar molecules. Even cows don't have that machinery, but they have microorganisms in their gut that do. And so the microorganisms take these cellulose molecules, snip them, make sugars out of them. So that's what the chewing their cud and the multiple stomach business, all that in a cow, allows them to digest the sugars in cellulose. For us, it's known as fiber, and I guess actually it's probably insoluble fiber. If you eat the cardboard box that contains your cereal, rather than the cereal, you're eating cellulose, and it goes right through you. We have no way of digesting it. What else about it? There's another sugar polymer that's also familiar that we can digest, and it's known as starch. It's just the way in which the sugar molecules are connected are different, and they therefore are ones we do have the machinery to snip apart, and so we can digest it, and it basically metabolizes just like sugar. So eating a chunk of, well, it doesn't taste very good, but a whole lot of starch and a whole lot of sugar are not very different. All right, so that's cellulose when you're burning wood in a fireplace. There's some other stuff in there, but it's mostly you're burning cellulose. So you're burning basically sugar molecules that are tacked one on the other. In this case, we're burning hydrocarbon molecules, paraffin wax. The difference between a sugar has oxygen in the molecule. Hydrocarbons do not. So these are, I'll talk a bit about how gasoline works when we get to automobile engines. But basically, we're taking molecules that consist of a long chain of carbon atoms all stuck together with strong chemical bonds so that it's one molecule, and decorated on the outside with hydrogen atoms. The whole thing is stuck together. But the whole thing is stuck together with a certain deficit of energy. And if you bring oxygen molecules from the air, which are also stuck together with a certain deficit of energy, into pairs, you bring those guys together and you rearrange them, you can end up with water molecules and carbon dioxide molecules. You basically use up all the carbons, all the hydrogens, all the oxygens. Everything's mixed and stirred, and out you come with water molecules and carbon dioxide molecules, which have larger deficits of energy than you started with. So the bonds that are formed in the burning process are stronger, involve giving away to the outside world even more energy than you began. And so we're turning these hydrocarbon molecules and oxygen in the air into water and carbon dioxide, and that process releases energy as the bonds get stronger in effect and involve bigger deficits. And that's showing up as light and heat. The light in a candle, incidentally, is glowing particles of carbon. Most of it is. So it's incandescently hot. We'll talk about that. That's thermal radiation you're seeing here. Okay, so the origin of thermal energy is this rearrangement of molecules. Tear apart the existing chemical bonds, rearrange them, put them back together, make stronger chemical bonds. The result, the energy that was released shows up, in this case, is just thermal energy. So, what else do I want to say with this? This is my same story about the bonds, the attractive and repulsive forces and the stable equilibrium. We will actually, at some point I may discuss, but it's not a central issue in the story, in what I'll tell you over the next week or two or three. But if you think about the two atoms sitting at thermal equilibrium, if they have a little extra energy around, they may not be motionless at equilibrium. They may instead be vibrating about equilibrium. We've done an awful lot of this kind of stuff in the past, right? An object on a spring bouncing around equilibrium, you on a trampoline bouncing around equilibrium. Atoms are bouncing around about equilibrium. So that's going on all the time. Vibrations around equilibrium. And it turns out the forces between two atoms, they are stiffer in that repulsive region where they're too close together than they are in the attractive region when they're too far apart. So if they vibrate about equilibrium, they bounce quickly off the moment when they were close together, and they take a while in the region when they're too far apart. So it's a quick bounce and then a long rebound, a long stretch. Quick bounce, long stretch. Quick bounce, long stretch. The result is, on average, they spend a lot of time farther apart than close together. Too far apart than too close together. The result is, the hotter you heat a pair of molecules, the harder you heat this bond, let's say, the farther apart the two atoms are on average. If you just average over time and just keep watching. And if you do this for lots and lots of atoms, as you increase the temperature of this collection of paired atoms or trios or quartets of atoms, all of the complicated, the hotter it gets, the more time they spend, the more they tend to spend time separated by more than equilibrium separation. What's the point of this? Stuff expands when you heat it. I hope you've noticed this in various contexts, that if you take almost anything and warm it up, as it gets hotter, as temperature rises, it gets larger. Not by very much, but by enough that it's an issue. So for example, if you heat up a piece of glass, a glass dish, for example, in the oven, as it gets hotter, the atoms that make up that pie plate or pan, that glass pan, on average, separate a little bit more. They just are spending more time beyond their equilibrium separation. And the pan gets a little bit larger. If you now take that pan and throw half of it into cold water in the sink, that portion that you cooled very quickly will shrink as the atoms return to their normal separations as best they can. The other half of the pan, being still hot, will stay large. And you'll be subjecting that pan to terrible stresses. And this is a way to break pans. So you don't take glass stuff right out of the oven and put cold water in it. What you're doing then is you're shrinking parts of it by stopping this. You they this bouncing process going on in part of it, and so the average separation is like this, and in the other part, you cool it, and they go to approximately the equilibrium separation. This section's small, this one's big, and you break the glass. Is that okay? I'm random wanderings. Okay. So this is the rearrangement process of starting with wood and oxygen, rearranging it, ending up with carbon dioxide and water, which are among the most common end products of burning stuff. Unless you're burning something exotic, you're almost surely producing water and carbon dioxide. One other tidbit with this, and that is a piece of wood just doesn't spontaneously burst into flames at room temperature. So the desk up here and stuff has been here for a while. Why isn't it burning? Since it's made of molecules that, if they were given a chance to react and rearrange with the oxygen in the air, they would produce molecules that have a bigger energy deficit, and therefore they would release energy. Why don't they do that? The issue is, to get that rearrangement started, you have to pay an initial energy price. Something's got to come in there, pull the existing molecules apart to some extent to allow them to reassemble in some more tightly bound form. And that input of energy to get the thing started is known as an activation energy. And in fact, you have to ignite the mixture. So you have to come in there with some source of initial energy to start the disassembly process. And that's why you have to light the fire. So the lighting process, what I'm doing right now, is I'm bringing in a source of thermal energy, a hot object, lots of thermal energy around. That energy goes into, in this case, the wax that we're burning, starts to disassemble some of those molecules, and the oxygen, and it gets them reacting, and then it's self-sustaining at this point. At this point, the reaction is proceeding all by itself because it's providing enough thermal energy to pay the activation energy for the next molecule to burn, which then pays the energy that the subsequent molecules need to burn, and so on. So combustion, or many reactions, require an activation energy. You've got to pay the piper up front. All right? So so now sort of a different question. Burning releases chemical potential energy. So just to name, to give a name to the form of energy that's present in the reactants, the molecules that you start with, even though it's we'll call it chemical potential energy. That would be a standard way of calling it. It is a negative. It involves a negative amount. I hope that doesn't bother you too much. The idea that an oxygen molecule has how much chemical potential energy does it start with? Well, it's actually, in principle, sort of a negative number. It's the deficit that you'd have to pay back to separate the two oxygen atoms. But when you're done, you're going to have the chemical potential energy of the burned results is going to be even lower. So you're going from a chemical potential energy that is a small negative number to a chemical potential energy that's a large negative number. That's a release of energy. So even if we work with negative numbers, it still works out that chemical reactions and burning tend to go from high chemical potential energy, even though it's negative, to low chemical potential energy, which is just simply more negative. So is that okay? Or questions about that idea? Work with negative numbers, it doesn't really matter. It's just you can lift the whole scale up if you like and just add a big number to the bottom and boost it up, and you're still going from higher energy to lower energy, higher chemical potential energy, to be specific, to lower chemical potential energy. Why don't you go backwards? So when burning happens and you release this chemical potential energy as thermal energy, why is it a one-way street? Why don't things ever unburn? Okay, as a question, how many think that it wouldn't conserve energy, unburning? Okay. How many think that it would violate the laws of motion? How many think that it would be statistically unlikely? Okay, we got about 50-50 between it wouldn't conserve energy and it would be it would be statistically unlikely. It turns out unburning would conserve energy. So once you burn something, like what I'm doing right now, okay, I'm burning this, and to the extent that nothing leaves this room, it's still in the room. We started with chemical potential energy, more chemical potential energy in the wax and the oxygen. The burning takes place, and we end up with less chemical potential energy in the water and carbon dioxide. The missing energy is out and about in the room as thermal energy. It's still here. If we close the doors and say no one can leave, it's still here. And so, in principle, if we could gather it together and bring it back here and shove it back into the flame and unburn the flame, we haven't, the long short of it is that we haven't lost any energy. The unburning process doesn't create or destroy energy, so it doesn't violate the conservation of energy. It also doesn't violate the laws of motion, which are pretty, they occur, there is the movement of the atoms and molecules. If you get it down there with a super microscope and you watch them, they're all obeying the laws of motion just fine. And they're indifferent to whether the reactions occur this way or whether they occur that way. The laws of motion don't care. And we're not violating those either. What we're violating in the idea of unburning the materials is the statistical laws. This burning process is the statistically likely process, given all the possibilities that could happen. It's a likely thing to have happen. The unburning process is statistically very, very, very unlikely. So unlikely that it never happens. I mean, you could, in principle, you could say, well, the chances are really small, but for all practical purposes, they are just completely opposed to it. So what's an example of something like this, a statistical problem? If you take a glass vase, you never know whether it's a vase or a vase. Take your pick. And you drop it on the floor, and it shatters. Well, you got broken vase there. In principle, if you take that broken vase up and repeat exactly the same dropping process you did with the vase, it could reassemble itself. The laws of motion don't care. The pieces bounce around. They conserve energy and momentum. Everything works out. It could, in principle, happen that the vase reassembles. This piece that was broken off that piece perfectly touches just the right spot. The bonds reform. The energy that was involved, what was coming in just right. It could all, in principle, happen. In practice, it never does because you know that's statistically so crazy unlikely it would never happen. You know, it's one thing to have two parts break apart and fly left and right. It's another for two parts to fly right and left, hit, and then come together. It would be like, well, I have various demonstrations of this sort of problem. Like one that I do, and I won't do it because it's so obvious. You start with a pile of blue beads and a pile of red beads on two sides of a big platter. That arrangement is a highly ordered arrangement. It doesn't happen by accident. If you just take a bag of blue beads and red beads, mix them together and pour them out, they're not going to do that. All red on one side, all blue on the other? You have to organize them, okay? You put the order in. Now you shake that thing and you put it down. I can guarantee it's not going to be red beads on one side, blue on the other. And you can keep shaking it all day, all year, all your life. You're never going to get them to separate. Not because it's forbidden by the laws of motion, but because it's so statistically unlikely that all the red beads would decide by accident to be over on this side and all the others on the other. Rosencrantz and Guildenstern are dead. Is that, anybody know that play anymore? Yeah. There's a flipping coin sequence in there where they flip its heads like 100 times in a row, which is just, it's a joke because it could happen, but it never does because it's so statistically unlikely it will never happen. So the same thing's happening with unburning. This process of starting with these high energy molecules, reassembling them, getting low energy molecules as a result, and sending the difference out as thermal energy is so disordering that thermal energy itself is so full of disorder, which we actually will name pretty soon. I'll name it now. The measure of disorder is known as entropy. Have you ever heard of that? This is what entropy really means. It's a quantity. It's a physical quantity. You actually can measure it. It's the measure of disorder. It's peculiar to be measuring disorder as opposed to measuring order, but that's the way it is. So you measure disorder. And once you've created disorder, entropy, you can't undo it. You can give it away. You can export it. But you can't like turn a disordered thing back into order and forever disappear the disorder. It's forever. Entropy is forever. You can make more of it. It's not a conserved quantity, so it's not a fixed amount. It's an increasing amount, or at least a never decreasing amount. You can't make it go away. So what we did when we burned this stuff is we created disorder that is now permanently present in our universe. You can never get rid of it. And you can't unburn stuff because that would get rid of the entropy. All right, long story. Long harangue, at least. Okay, so we've made the thermal energy. At the biggest level, we've converted what was ordered energy in the presence of those chemicals into disordered energy, which is thermal energy. Now we have to give it to the room. And so one of the biggest parts of the story then is finally how the wood stove transfers its thermal energy to the room. So it's made it by burning the wood. There are issues about where it gets its air and where it gets rid of its chemical reactants. the advantage, I should say, of a wood stove over most of the other kinds of heating units that use combustion is they draw air, they draw in oxygen from the room or from somewhere pretty strategically, so they're not just squandering warm room air, for example, pulling it into the fire. And they're also careful about where they put the reactants, because you usually don't want to be breathing the burned air, the burned wood, not because carbon dioxide and water are fine, it's the other junk that burns with wood. You don't want to be breathing it, so they send that up a chimney and out of a house. So they do a pretty nice job of producing the thermal energy without upsetting your environment, the living environment. But there is still the issue of getting the thermal energy out of the wood stove into the room without getting the junk, like the smoke, into the room. And so they use mechanisms of heat transfer, and that's sort of my central story. It turns out heat flows from hotter objects to colder objects. That turns out to be a statistically driven thing too. So if you've got a wood stove that's full of thermal energy and consequently it's got a lot of thermal energy per, in effect it's sort of per particle. That's a little bit of a oversimplification. But if it's got a lot of thermal energy per particle being atom or something like an atom, then it's hot. It has a high temperature. And if it's the hottest thing in the room, which it probably is, then heat flows from it to the rest of the room. So I should say, it is heat flowing from the thermal energy in the stove migrates as heat into the rest of the room. And it does this for statistical reasons. That as heat flows from a hotter place to a colder place, that actually disorders the system a little bit. It's going to create entropy. We'll see this when I talk about thermodynamics. And it's a one-way process. The heat flows from hotter to colder. It creates more disorder. You can't uncreate the disorder. So this happens and it can never go back. So another way of thinking of that is that if you've got hot molecules and stuff over here, there's a lot of jittering and jiggling of the particles. The thermal energy is real. It's actually there in the motion of the tiny particles. You can't see it because they're tiny. And if you've got another section over here in which the particles, the system is cold, its temperature's low, that thermal motion is much less aggressive. And if you bring these in some manner into contact with one another, so they're just, the ones on the hot side are jostling a lot, and the ones on the cold side are jostling only a little. I mean, just think of it as life on a subway platform or in a bus, an overcrowded bus or metro. The ones that are jiggling like crazy, they're going to tend to bump the ones that are just sort of standing there trying to be kind of calm. And pretty soon, the jiggling motion will migrate statistically from the aggressively moving guys to the not so aggressively moving guys. It's just more likely. It's not, the one who's barely moving is just not going to jostle the other ones very much and convey to them this thermal motion. All right, so it migrates from hotter to colder. That's the bottom line. And so what temperature does for us is it orders our world, it ranks our world or something like that, between things that tend to give away thermal energy as heat to things that tend to receive it. The hotter they are, the higher their temperature is, the more they tend to give away thermal energy to the things around them. And the colder they are, the more they tend to receive it. And so if you went through this whole room or maybe the whole building and you sort of brought together every possible pair of objects, you could say this one always gives heat to that one gives heat to this one. You could put them all in order. Which one is the biggest giver, which one's the biggest taker, and everything in between. A temperature scale simplifies that. You can just go and measure the temperature of all the objects in our environment, and you will know that whenever you find one object that is colder in temperature than another, when you bring them together and allow them to exchange heat, heat will always go from the hotter one to the colder one. It's just driven by statistics. All right? Question about that idea? So that brings then the issue of how does the heat go from one to the other. And there are three main ways in which, this is just about the value of using a wood stove as opposed to just lighting a fire in the middle of your room, which has obvious disadvantages. I do not recommend you do it. The three transfer mechanisms, you probably have encountered these at some point or other, but primarily as a name. So my job is to bring reality to them. The ways in which heat transfers from hotter objects to colder objects is by way of conduction, convection, and radiation. Hopefully these are sort of familiar as names, at least. Conduction is the transfer of heat through a material. You don't actually transfer the material itself, but the heat moves in some manner or other through the material. So for example, if you hold a piece of copper, a copper rod in a fire, you put it in the wood stove and poke around for a while, it's going to get real hot. It's going to transfer a lot of heat to your hand. Heat's going to come rushing through the copper without the copper actually moving or anything in it rearranging permanently. But the heat will come roaring through to your colder hand and burn your hands. That's conduction. Convection, and demos I don't have time to do, but convection is the movement of heat in a moving material. And for it to be a moving material, it's typically got to be a fluid, so a liquid or a gas. Convection, I guess I can name things, along with names to identify situations in which it happens. If you go and you touch the surface of the wood stove, you will feel a lot of heat going into your hand by way of conduction through the metal of the wood stove. Okay. Convection is the movement of heat in a fluid, often driven by buoyant forces, which we'll come to. And you get this in the context of a wood stove by putting your hand over the wood stove. You feel heat rising off of it. It's rising in the form of heated air moving upward. It's lifted by buoyant forces. Hot air rises. So we'll talk about that. The last way in which heat moves is the most exotic, and that is by radiation. And radiation, the name is a catch-all for basically anything that is traveling en route. So right now I'm human radiation, okay, heading out the door. You wish, okay. But just as a sort of public service announcement, radiation, there's so many different radiations. So say radiation is dangerous is a wild overstatement. It's lumping together all kinds of different things. Rain is water radiation from the sky. The radiation that's referred to here is electromagnetic radiation. So it is the same type of radiation that is light, that is radio waves, microwaves. It actually also includes seemingly more threatening ones like X-rays and gamma rays. It's an entire spectrum of waves, some of which are more dangerous than others, and some of which are just innocuous. And the thermal radiation that we're dealing with in this, that we will deal with in this class, are very innocuous. It's just, it's primarily infrared portion of the light spectrum and doesn't do much except transfer heat. So it's innocuous radiation. Anyway, the radiation where you see that or feel that in the context of a wood stove is when you stand away from it. So there it is glowing. There it is glowing away. I'm saying glowing, but you can't see it with your eyes, but you can feel it with your skin. If you stand near the wood stove, you feel, ooh, I feel something warm coming at me. And if you block it with your hand, you can actually, you feel the shadow. It's a glow. If a wood stove doesn't do it for you, think of a glowing fire, a fire where you got nice coals there. Those coals that are glowing orange, that is their thermal radiation. But the lion's share of their glow is actually not visible to your eyes. You're just seeing the tip of the iceberg in that orange glow. And if you're looking at those coals and you're feeling the heat on your face, you're feeling the thermal radiation, and you can block it with your hands because it's like light. Your hands cast a shadow in it. I have all these demos that I'll have to do next time, but I can show you things like this is a heated block here. And oddly enough, the face of this block that we're staring at with this device that sees thermal radiation, it's a black surface. And that this thermal radiation sensor is seeing a lot of that thermal radiation. If I block it with my hands, it goes down. It's actually seeing the glow off that black surface. So that's thermal radiation being transferred by radiation. We'll play with this another day where we'll watch thermal radiation crawl out some sticks. This last thing just to show you here, I'll just flip this guy on because I can, is this just projects thermal radiation. I got to turn that off. Side projector, no signal. Okay. You're seeing a filament here that we're going to heat in the presence of water. And when I heat that filament electrically like this, you see the hot water rising? That's convection. So next time I'll work on conduction, watching heat flow through materials, convection, watching heat flow with materials, and radiation, watching heat flow by way of light and all light's buddies. All right, thanks for sticking around and have a good weekend.